Questions? I have questions. Tucker? No, you're not. Did you do your chapter 1 stuff? A couple of you did not. Tom? What's up?
What?
What's up with your chapter 1 stuff that was due?
Did I not turn it in?
I did not see you turn in your lab, but I do not have that from you. I do not have it from Abby. Where's yours?
I didn't quite get to it.
Okay, I've already put zeros down for you guys. I'm serious. We need to stay with the program from the beginning. I'm not going to let you get behind. This is a due date. If this was your job, what would Nick, same with you. What's up with that, Nick? Is your mic working? I'm not hearing you. I see you working. I saw you, so I'm working on it. Is that what you said? Yeah, it's not working. So if this was your job and you said, oh, I didn't do the stuff I was supposed to do, you'd get fired right away. And I have to fill out stuff soon about your grades. And if your grades are low, you're going to get dropped from the class. Okay, because within like a couple of days, I'm going to be putting in your beginning grades. And if I'm getting zeros, then you're not doing the assignment and you're going to get contacted. So make up for that now and then do not turn in anything late again. Okay, dead serious. Dead serious. Now, as far as the worksheets, you guys, most of the comments I gave you, I tried to give you whatever comments were pertinent. You need to do more diagrams. Some of you had, a couple of you had really nice diagrams, but most of you came up short, and you may be saying, well, I didn't really need to do that. You need to get in the habit of putting them in there where they're appropriate. If you're doing the temperature profile of the atmosphere, or the layers of the atmosphere, that's an obvious one that you should be able to put in with the diagram. Some of you did those diagrams in the math lab, which is not what I meant, but I get what you're saying. I'm being a little bit nice with you. I didn't take off a lot of points if you didn't have enough diagrams, but I will next time if it goes to needs improvement. Okay, so I'm dead serious about putting the professional notes together. So I gave you feedback on that stuff. Whatever feedback I gave you is important, and I'm giving you a little bit of slack the first week, but next time it's not going to be. So next week it's chapter 2, right? Chapter 2 outlines. Lena, you already done it?
Yeah, I have like 2 more to go.
Okay, I assume that. See, I know Lena, so that's what good students do. They're working, they get ahead so you don't get behind. Okay, so take that. Any questions on that outline stuff, or not the outline, but the notes, the questions for the worksheets on the chapters? Any question on that? Anything that you didn't understand from that? Take out your lab, because that one is the one that we need to go through. Because I don't think you did. There was a couple people, I don't remember who it was offhand, but somebody has said, you did a good job, but you still made a lot of mistakes that they're not what I want them to be. So this first page of the lab is talking about variables, talking about the equation, cause and effect, dependent, independent variables, directly, inversely proportional. Then you started writing down the equation. So all of this stuff is what we did in class. Now we talked about this, and you were supposed to say, if pressure equals force times area, you were supposed to write down pressure and force are directly proportional if area is constant, pressure is inversely proportional to area if force is constant, and force and area are directly proportional if pressure is constant. And that's the same thing with the other ones. Make sure that dx in your mind is distance, not change in distance, so that the velocity is directly proportional to the distance in the same amount of time. Now, and there's three other ones, right? There's two other versions of this. So listen to what I'm saying. Velocity is directly proportional to distance in the same amount of time. That is not a good way to speak. So what I say is going faster means you're going to go a greater distance, like you're going faster if you go a greater distance in the same amount of time. So you really want to use adjectives that describe what we're talking about, like a stronger force, a heavier mass, or a greater distance, something along those lines, in the same amount of time. And when I say the amount of time, what's a better word? What's a better word?
Duration.
In some duration. Okay, you could say duration, you could say period. So one of those two things is what you should be doing. Okay, so that's what I wanted you to do here. A lot of you left this section blank. And okay, how many of you left that Oh, I didn't share the screen. You didn't tell me I didn't share the screen. How many of you left this section blank right here?
Oh, I did.
Why is that? Tim, you don't seem to be a person who would not do that on purpose.
I think that's what it is. I think I just missed it.
Yeah, okay, so what that means to me is, and again, I look for stuff like this, right? And I say, okay, you need to read through the lab. Don't just put the answers in place. You'll have to trust me on this. You need to go read through stuff so that you know exactly what's going on. Now, this one here, Nick or Zach, was it you? Who was it that had some weird stuff in here? Was it you, Zach, or was it? I don't know. Anybody? Did I put a question mark here or something? Do you have my notes? Do you see my notes on Blackboard when I return them? I don't even know what that looks like to you as a student, but yeah, you see the stuff I say to you. And then sometimes, I don't do it a lot, but sometimes I'll write on here, like I'll make a blue X or something. Or some of you had a question mark. Do you see that? Are you looking at yours? Everybody say yes or no, nod or shake your head. Are you looking at this?
I'm looking at the file I submitted, but I don't see like the one that you sent back to me with the comments.
Well, the comments will either be on the side by, like in the text, or sometimes I write something on here. I may not have. Maybe it's not you, Zach, who I'm thinking of.
Okay, yeah, maybe not then.
Over here, so we talked about this equation. We talked about a gradient is a change in something over a distance, right? And this is a horizontal distance, the one on the left, and this one over here is a vertical distance. So a temperature gradient is a change in temperature over a distance. So in here, what would you have written? Well, you would have written one of two things. You would have written or you would have written dt dx. Okay, how many people wrote this one? Raise your hand if you wrote that as the answer. You did, right? What did you write this? Who wrote this one? Okay, there was a bunch of people who didn't raise their hand. What is, Isaac, what'd you put?
I was looking for mine while you were asking, but I put change
This first one?
E over change over X. Yeah, I did the first one.
Okay, so why would I choose this over that? Well, I mean, it's because I put in the delta here. Can you at least understand that those two are the same?
Mm-hmm.
As far as you're concerned, that's exactly the same thing. So a temperature gradient is dt dx. Now, what's a vertical temperature gradient?
Pt.2.
Okay, so you would say this, right? I mean, you could have said delta T over delta C.
Or delta, yeah.
I mean, it doesn't, again, if I asked you this and you gave me either of those two answers, you're correct. I don't necessarily favor one over the other. But if I see this, what then is another name for a vertical temperature gradient? Raise your hand, don't say it. Raise your hand if you think you know the answer. What is another name for a vertical temperature gradient? Do you think you know what it is? Aaron, do you know what it is?
Okay, what?
Is she?
She's she's spelling something.
Okay. Let's give Aaron a second here.
She says up front.
No. Tim, what were you gonna say?
Maybe a lapse rate.
Yeah. So a vertical temperature gradient is also a lapse rate. Now we define the lapse rate, gamma. We define it, and the only thing that's different is we put in a negative of this because it's a rate of cooling. But you understand that a lapse rate is the vertical temperature gradient. In other words, the temperature changes as you go up in the atmosphere. That temperature gradient is the lapse rate. They're the same thing. When I talk about steep lapse rates, that's the word I would use, steep, big lapse rates. That means there's a big temperature gradient. And a big temperature gradient means over some distance, this is changing, the temperature changes by a lot. Given a certain distance in vertical distance, there is a bigger temperature change, which leads to a larger lapse rate. Now, Sam, you should know this from your experience that big lapse rates in the atmosphere indicate instability. This is what we're going to be eventually getting to, is getting thunderstorms, which is related to lapse rate. Okay. Now, a vertical temperature gradient would be the same thing, except instead of temperature, what do? We put in pressure. And then what does it mean if we call this a pressure gradient? Then A equals B over C. Do you see that? What's the two ways to have a strong? In other words, this is big if I have a bigger pressure change over some distance, or the same pressure change over a smaller distance. And this is in the vertical. In the horizontal, do you agree it would be this? That's a pressure gradient. Okay, so I'm going to stop for just a quick second. Go over here to a page, and I'm going to show you. Hold on, Sam, you're here. I'm going to go over here and show you in the models a map that looks like this. And what we see on here, these lines are called isobars. An isobar is a line of constant pressure. And I believe this is in your reading. So we're going to do a lot of time with this later in the semester. But for now, I just want you to see this. Now, this isobar here is labeled 1000 or 10, what is it? 1024. This one is 1026. This one is 1028, something like that. This is probably not the best. In fact, let me do this. Hold on a second. You're probably going, what the hell are you doing, Paul? Here, they're labeled up here. So 1028, do you see them up here? 1028 and 1026.
Can you see him?
So this is 1028. And the difference between the isobars in terms of the pressure is 2 millibars, right? The pressure change from one isobar to the next is 2 millibars. So what I could say in this scenario is that the pressure change is 2 millibars. And then I go, well, from here to here, do you agree that is some distance delta x?
Right.
That might be 100 miles, something like this. So my pressure gradient is 2 millibars in 100 miles. Look at over here. What's the difference in the pressure between isobars over here? Well, it's still 2 millibars, right? But what about the distance between them? Do you agree it's going to be a smaller distance, which makes the pressure gradient what? Much larger.
Steeper.
Isobars close together, a larger pressure gradient. That pressure gradient,
And
by the way,
stronger the wind.
tells me how strong the winds are, right? So I've got these isobars close together. I know it's going to be windy. When they're not that far apart, it's not that bad. So watch this. Here's our forecast. Look at how close the isobars are here. They're very close together across Illinois. This is coming up Friday, Thursday night. And look at the temperatures. Going to be stinking cold. So not only is it going to be really cold, it's going to be windy and cold, which means our wind chills are going to really start to tank on Friday. We have a strong pressure gradient. A strong pressure gradient means the winds are faster. Faster winds, cold temperatures, it's going to feel miserable. So we're getting into winter, and it's going to stick around for at least a week, where we just keep getting. If you take a look at these temperatures here, and actually let me show you something. I'm going to go a little bit above the ground.
You know it's a strong system when it curls around the low.
Yeah, absolutely. So here, look at this. This is real. The green is this really cold air. I think it's coming in at. This is about a mile above the ground, negative 30 C. So lots of cold air stays in place. And then it's not as bad, but there's a lot of cold air coming over the next week plus. So winter is going to be horrible. And if I show you this, remember we talked about a time series from this one? I'm looking at a time series. Here's the time on the horizontal axis. Oops. There's the time on the abscissa. Here's the ordinate is the amount of snowfall. So we see coming here in the Chicago area, somewhere around 2 to 4 inches of new snow coming through. But the really bad thing is the temperatures do this. Look at this. Temperatures are going up and down a little bit, and then they crash. And then they crash even further on the weekend, somewhere in the negative teens, probably. It's going to be windy too. So what do you think that's going to do? That's going to lead to the wind chills. Look at the winds out there. So this is what we call the feels like, or the apparent temperature, or the wind chill. Now we're looking at temperatures that are in the negative 30 to 50 degree range for the weekend. So Tim, you said you were doing a lot of shoveling?
Yeah.
What's really going to suck is we get this snow. It's going to be really wet. It's going to flash freeze. It's going to become very heavy and icy. And when we're out trying to shovel Friday morning, it's going to be like wind chills of 20 degrees below zero.
Can't wait.
So it's going to be exciting. Okay, so that's our forecast. Because I figure we are in intro to meteorology. We probably ought to talk about the weather a little bit. And how many of you say you like winter? Yeah, Nina, you're crazy. Come shovel my driveway, okay?
I know. I'm worried for ice fishing because I want to go this weekend, but that's going to be miserable. So I'm not.
Yeah, that would be bad. I'd wait a weekend.
Yep.
Okay, so that's what's going on in the lab so far. Any questions up to this point? Here we talked about the lapse rate. And then we talked about the lapse rate. If the temperatures were switched, we would have an inversion, negative lapse rate. Over here, you were calculating the lapse rates. I think you had a fine time on that. And then you're just plotting the temperature. So 27, 20, 22, and 12. And then all you would do on this is you connect. This is what you need to do. You need to connect the dots. because that's showing you the temperature profile of the of this layer of the atmosphere. Now, when you compare this to what we drew the other day, where we had the tropopause and then, or the troposphere, the tropopause, and the stratosphere, right? So this is the stratosphere, that's the troposphere. We said that the average lapse rate was 6.5 degrees Celsius per kilometer. That's on average. In reality, the temperatures change quite a bit within the troposphere. So what I asked you in this next question was, what's the inversion layer in the above graph? And clearly the inversion exists from 1 to 2 kilometers, right? Now, how do we know that? Well, we already said in this space, this was an isotherm, and we labeled the isotherm dT/dz equals 0 on that line. And this inversion is showing me a line that's going in this direction. So it's negative. And in this direction, it's going to be positive, right? We kind of did that. Now, I asked you, I asked you, what's the relationship between the slope of the lines and the lapse rate? And I said, use diagrams rather than words. And I didn't count off if you got this wrong, because all of you would have had points taken off. But what is the answer? How would you describe this best? Okay, look at this green line. This green line is an inversion. Do you agree? This pink line is a positive lapse rate. Do you agree that the green line is getting warmer as you go higher? The pink line is getting colder. What's the blue line? What's true about the blue being on the blue line?
It's constant.
It's constant. So what do we call the blue line? Abhi? What do we call the blue line in this diagram?
I mean, it's the constant line, but
It's a line of constant what?
temperature?
Do you remember we just talked about lines where the pressure is constant? What's that called?
Um,
When I was showing you the weather maps, we called them that. What are those? Anybody? Just go ahead and talk.
last rate?
Isobar.
No, on the maps that we showed you? Who said it?
It's an pressure is isobar. That's an
Isobar. So if this is constant, that was constant pressure. What's this line then?
Isotherm.
This is an isotherm. So if the temperature doesn't change, if it's constant, then what we're saying is that the line that we draw is an isotherm. So watch this, guys. Ready? What's the lapse rate of this yellow line? 0, right? What's the lapse rate of this line? Best you can come up with, negative. What's the lapse rate of this line? Positive. So if this is negative, 0, and positive, what's happening to the values of the lapse rate the more this way that I go?
It's steeper.
It's steeper. It's a bigger lapse rate, right? So what I can say is this is negative, this is 0, this is positive. It's getting more positive this way that I go. So what you would answer is that the more, oh, sorry, let me do this color. That arrow indicates an increasing lapse rate. So I don't want to deal with slope. But this type of diagram says it's an increasing lapse rate. Now, Tom, I think it was you. Didn't you put in a diagram? The only thing is, did you see one that says isotherm in your diagram?
I'm not sure if I did. I wasn't really looking for it.
You have, where's your lab? Somebody put
I
it
was
in.
trying to find it.
Let me see if I can help find that.
I have my lab, but I didn't find a picture with an isotherm.
I thought it was you, but maybe it was somebody else. Because, but I thought it was you. Here, I think this was the diagram people put in. Did anybody put this in there? Tom, that wasn't you? That was you.
That was me. I have that.
I thought, where did you get that? That was interesting that you put that in there.
Just Google Images,
Okay, so you did kind of the same thing I just did, right?
more or less.
Unfortunately, this is based on adiabatic. So what is that supposed to mean? Did we do the dry adiabatic lapse rate yet? No, we haven't done that yet. Okay, so I don't want to do that. So just, I appreciated what you were doing. I think it's good. But do you agree that the lines are going this way become a greater lapse rate? And we'll deal with this term adiabatic coming up. That's coming up today. But I just wanted to kind of point that out because it was an interesting thing that you wrote there. So does that make sense that the answer to that question that I said, draw a diagram in your lab, is really this type of a diagram where you've got two lines and you're saying the more this way the line, the greater the lapse rate. So let me redraw. I'm going to draw two lines. And I'm going to call this line A, without drawing lines. That's line A, and that's line B. Which of these two, line A or line B, has a greater lapse rate? On the count of three, everybody. Mic's off, or mic's on, I should say. On the count of three, give me the answer, A or B. Which has a greater lapse rate? 1, 2, 3.
A.
A.
Okay. Can you explain, using A equals B over C, why it's a greater lapse rate? Ryan, what do you think, buddy?
Using A equals B over C.
Yes.
I don't really know how to explain it that way. I
Okay.
just know the slope is going to be higher.
Well, you can't use slope because slope is rise over run. And rise over run is only best when you have the independent variable on the abscissa, which we don't have. So I don't want to use the word slope. So I'm going to see, remember I talked about level 3 understanding? Level 1 is I talk, you go yes. Level 2 is you kind of get it. Now I haven't seen a lot of light bulb moments because you haven't figured stuff out. You're sort of, you don't know if you're in level 1 or 2. But you're probably not level 3 because you would be able to explain this. So you need to get to level 3 understanding, which means you have to go through it and work it out loud and talk to each other. So I'm going to break you guys up into 3 groups, and you will discuss how you can demonstrate and explain to other people in the classroom when we come back together why A is a greater lapse rate. You have to show me using the formula A equals B over C. Using what it means to have a greater lapse rate or a greater temperature gradient. In this case, a vertical temperature gradient. Does everybody understand what I'm saying? let's do this. Breakout rooms. I'm going to break 3 rooms. You guys will be good. Good luck. How'd you guys do?
Little rough. What I thought of was like the reason why it would have a greater lapse rate is because it's like further away from the constant 0, but I don't know how to like translate that to relate it to the equation of A equals B over C.
Okay.
Yeah, that's as far as I got.
How'd you guys do? Isaac, what about your room?
I'll be honest, I wasn't really the one discussing much. It was more of the other 2 group members.
Who are
I
the
don't
other 2 in your room?
understand it that well.
Tom?
It was me and Sam, and I basically said that A is greater because it's getting more cold over the same change in height. So
Okay, stop. Listen to what he just said. Say it again.
getting more cold over the same change in height.
When he says that, it's getting more cold over the same change in height. Do you see that on here? Do you see that on there? It's getting more cold over the same change in height. How do you do? So Tom obviously sees that. What do you guys see? Like, can you express what that means?
Yeah, it moves further left.
So now Lena said, right, you said, well, why don't you could put in some values. I don't want to put in values. So let's do this. What is this? What is this?
Surface temperature.
Everybody, what is this?
A point.
Okay, what is a point?
An ordered pair.
Thank you, Sam. An ordered pair. Do you understand that we are implying that there are axes on this graph, and this graph axis is temperature, and this graph is height. This axis is height. So this point has a T. What T is it? I don't know, some value T. What height is it? I don't know, some value Z. Now you could say Z is 0, that's fine, but do you understand it's some value? The B line goes to this point. What point is that? What's this point? Lena? What's the value of that point? Isn't it some value T? And some value Z?
DTDZ.
Is this the same T?
No,
Is this the same Z?
no.
Okay, so this is a delta T, and this is a delta Z. From there to there, from there to there, right? Let's do another point. Let's go to the A line. What's that point? Do you agree that's some point T? What's the height? Some green Z, right? What is this distance? Isn't that some change in temperature? What's this distance?
Change in height.
But between the A line and the B line, do you agree that in both of those, the lapse rate is a change in temperature over the change in height? For A, what's the same in both?
Height.
The change in height is the same in both. Which has a bigger delta T, the A line or the B line?
The A.
That's bigger. So when the temperature change is bigger over the same change in height, you have a bigger lapse rate. See, this, guys, is how you learn to think. You put together the mathematics to express what you kind of know to be true. So, Tim, you were doing the same thing. You were right in what you were thinking. Tom, you were right in saying it gets colder more for the same change in height. Now, obviously, Tom has had more math than a lot of you, but that's the kind of thing that you develop in math. Your thinking is better. And we don't want just math and science are not totally disconnected. You have to have one with the other. The problem is math, I think, you forget that there's actually a physical process that you can understand. Like, you know what a change in temperature is. You know what a change in height is. If I were to give you this with X's and Y's, you would go, I don't even know what you're talking about. Does that make sense?
Makes sense. Yeah.
Okay. Does that help you learn this better graphically? So right now, show me with your arm a lapse rate of 0 degrees Celsius per kilometer. Right? It's going to be straight up and down. Show me a negative lapse rate. See, I don't. Here, I'm going to do it this way. There's 0. That's a negative lapse rate. Does that make sense? And then that's a positive lapse rate. And the more this way, see, a lot of you, I don't know if your camera is a mirror or if it's a camera. And so do me a favor, everybody point to the right, to your right. Point to your right. Okay, so I guess everybody's pointing the same direction. So that means this line, an inversion should go to your right. And this should go to your left. That's a positive lapse rate. And the more this way, the greater the lapse rate. Now, this is super important. Can you write that down? Can you write down that information? I hope so. Okay, now in here you did this. I think most of you did this fine for the most part. Couple problems. Let me just show you something that you need to do. So I'm going to click on one of these links and go to a page. Okay, and so on this page, I have the 850 at 5.6, 1507. So the temperature at 850 millibars is 5.6, and the height of 850 millibars. In other words, to go up to that pressure, 850 millibars, I go up 1,507 meters above the ground. So we would say AGL, above ground level. Actually, no, I lied. Above sea level. But this is not that big of a deal. Now, what's the temperature at 700 millibars? What does it say? Negative 1.5? What's the height of 700 millibars? 3079. Now I'm saying, what's the lapse rate between 850 and 700 millibars? And the answer is, I want the change in the temperature divided by the change in the height. Well, the change in the temperature is 5.6, 6.6, 7.1 degrees. Do you agree that's the difference between those two? Divided by the difference between those two, which is going to be 1,572 meters. Notice I don't care which one I subtract from what. I'm looking at just the difference. Differences are always positive differences, like an absolute value. But if it's getting colder, then I'm going to plug a negative in here. I mean, a positive. If it's getting warmer, you go higher. And do you agree this is going higher? Then it would be, and is it getting colder the higher up I go? Yes. So the lapse rate is positive. Now, some of you did this and you got some weird degrees Celsius per kilometer. But what is the unit of a lapse rate? It should be degrees Celsius per, I'm sorry, you did degrees Celsius per meter. It should be degrees Celsius per kilometer. So 1,572 meters is actually 1.572 kilometers. So 7.1 divided by that, and now it gets you whatever that is. So it's 5 point something. Does that make sense? So some of you did degrees Celsius per meter. That's going to get you a 0.00 something. That's bad. I didn't care about that as much, but the positive sign or the negative sign was important. And some of you were getting that backwards. So do you feel better about getting the positive and the negative sign?
Mm-hmm.
Okay. All right. That, and then you do the same thing for the next one, which I think you did. So that's how you do the lab. Be prepared for that on the test. Get rid of that. Get rid of this. And then that's the end of the lab. So that goes through all the answers for the lab. So that's what this lecture will be, or part of it. Any questions on that?
Any questions?
Okay. So now we go to here. I'm going to go with the black screen because I like it better. I have a parcel of air. What kind of a box is this?
Imaginary.
It is imaginary. What's its name? What do we call it?
Evan McAllister.
No, this is a what box?
Vegas.
It's a Vegas box. Because what's in the box stays in the box. Now, do you agree that in the box, there are some characteristics of the box? Do you agree there's pressure? What is the pressure inside the box?
Pressure in the box.
The pressure inside the box. What is the pressure outside the box? The pressure outside the box. Why is there pressure outside the box? Because there's air outside the box. There's molecules. What is our working definition of air pressure? Listen to the words I said, folks. Put this into your memory. What is the working definition of air pressure?
It's the weight of air above you.
It's the weight of the air above you. That's our working definition. What in reality is the pressure inside the box a result of? How would you answer that question? What is the pressure inside the box the result of?
H.
Lena?
Oh,
Is it a result of could it be like temperature change?
What I'm asking for is that, do you agree that there's air pressure in the box?
Yes.
What exactly is causing this thing we call pressure? Tim, you want to go for it?
well, I know it's equal to the pressure outside of the box.
It is, because what's the box made out of?
Nothing, I don't know.
Right, it's no, well, it's made out of your what?
Hmm?
What is it made out of, everybody? Your
Nothing.
imagination, right?
No.
The box is imaginary. There is no box. It's just a collection of air. And there's air inside the box and there's air outside the box. This is in your imagination. So there's no real box. But what is the pressure in the box? Define what the pressure is. Like I could say, you know, describe who you are, Tim. And you can say, well, my name is Tim. That's not what I'm saying. I'm not asking you the name. I'm asking you, what are you? What are you? And then you'd have to describe it. So what is the pressure in the box? Zach?
like, so we're assuming that the box is like you can't, like the pressure is like different from inside and outside the box, right? I'm just confused. Or it's like,
No. Somebody responded. Who said it? Who was talking? I need to do this. Oh, actually, I can do this. What'd you say? Zach, it's you, your mic seemed to be cutting out a little bit.
oh, mine? Sorry. So I'm just a little bit confused on like, so is it like what we were doing before with like the imaginary box and how like the pressure
It's an imaginary box.
So the pressure is the same inside and outside.
But what is the pressure inside the box? Don't give me the value. I'm not asking for its name. You're telling me that the pressure inside the box is PI, and you're telling me that it's the same as the outside pressure. That's all true. I'm saying, what is the pressure? What causes the pressure? Why is there this thing called pressure?
It's the force over area.
Be more specific.
So it's the interactions of like the molecules inside bouncing off the walls.
Okay,
Box.
now be more specific. See what's happening, guys, and this is true. Okay, remember how many years I've taught. I want you to think about this. This is like my 32nd year teaching. 32 years. I have. Do you know how many students I've had in my life? So when I talk to students and they talk to me, I get to know them. Do you agree? I get to know how students think for 32 years. So nothing surprises me about the way you think. What you need to start doing is you have to own the knowledge, right? You need to own the knowledge. And what happens too much, Tim, and there's a couple of you guys who aren't like that. You're too passive. You're waiting for information to be given to you. And that information might be my lecture. It might be your reading. You might answer questions, and you're trying to just give me the information and not keep it in my head. What I'm saying is you need to externalize it. You need to communicate that information because that's level 3 understanding. So I'm saying, what is pressure? Now, Zach said something about the molecules hitting the walls of the box, and that is not untrue. But can you give me more specific idea of what pressure is? Define it as though you're teaching a college class with people who are really smart.
Like, so in my own words, how I describe pressure is like the force of air and how much we pack into a limited space. And because like going back to like what you were saying about like how they make grenades is that like they have like the reaction on the inside and it bursts. So I usually think when I think of pressure, I think of like how it bursts open. So I think about like a lot of like just anything packed into a limited space. And if you have and like the exact opposite too, we would have a vacuum if you take away objects from a limited space.
I understand what you're saying. It's you're kind of defining more in terms of density, but I want it more in terms of what pressure is. How about it, Ryan? Can you do that?
So to define pressure, I would say, like, I guess if the molecules are moving faster and bumping into each other, there's more pressure. Or if you can change.
Now listen here, Ryan, and because Lena, you did kind of the same thing. Now you're telling me what causes the change in pressure. So you're saying if there is a greater temperature, they'll move faster. Fine.
Yeah.
You're not wrong, but you're not defining what the pressure is. You're not explaining what the pressure is. Have you ever dealt with a boss who says, you have a question, they're trying to teach you how to do something, and you're like, okay, tell me what to do. And they're giving you all this other information. I'm like, no. Just tell me what this is. Define this. Tell me what this is. I don't know if you've ever had a situation like that. Nick, you know what I'm talking about?
Oh no, can I try to answer it?
Yeah, go ahead.
Pressure. All right, so are you trying to get us to say that it's the amount of force put on the box, like the sides of the box?
Which makes it a what?
Wait a minute.
You said it's how much force is on the sides of the box is really the what? What is the side of a box? Isaac, what is the side of a box?
Is it a wall?
What is a wall? In this idea, what are we trying to define that to be?
It's like a surface, sort of.
Close. Surface what?
Area.
It's an area. It's how much force is acting on that the areas of each wall. How many walls are there?
4.
No. 3-dimensional box.
Oh, right.
1, 2, 3. So you have 6 areas, right? 6 sides of the box. This side, these 2 sides, these 2 sides, these 2 sides. So it's how much force is acting on that area. Well, duh, didn't we already say that pressure is force over area? That's what we said. But what exactly is the force? I'm saying define it. Avi, what's the force?
Would it? I feel like I would be repeating what they said, but then would it be the molecules pushing against the surface area? Isn't that the force?
And what happens to the molecule when it does that? What makes the force imparted? I mean,
The pressure
you're
inside
not
the
wrong.
box?
No, now you're just defining what the force is. Aaron, does Aaron have an answer? What's the word I'm looking for?
Momentum.
And it's not just the momentum, it's the what of momentum.
Change in momentum?
It's the change in the momentum over it's the fact that the molecule changes its momentum over in a what?
In a period of time.
In a period of time. Isn't that what it is? So here, let me do this. Oops. Where are you guys? So what I'm saying is that I have a change in the momentum in a given amount of time, which we've defined to be the force, right? So this molecule hits the wall. And this derives itself all the way to F equals ma, right? Force equals mass times acceleration, which is Newton's second law, right? Do you know what Newton's third law is? It's the most common one that you probably know. For every action,
There's a reaction.
there's a reaction. There's an equal and opposite. So the idea that the molecule hits the wall of the box, and when it comes back, the wall is, if the molecule is hitting the wall is hitting the molecule. And the molecule goes back. It's changing its momentum. Is it changing its mass? No, it's changing its velocity. So really it's dv dt, which is equal to ma. dv dt is the acceleration. It's a change in the velocity. Now here's the thing. What is velocity?
Speed and direction.
It's speed and direction. So does the speed change when it hits the wall? The direction does. Okay, so that's the pressure. Now Lena, or whoever was talking about, do you agree that if these molecules are moving faster, they will hit with the greater force? their momentum will change by more, which means you're going to increase the pressure because the pressure is force over area. A equals B over C. By making them hit harder, by making them change the momentum more. Do you see how this is A equals B over C? This is A equals B over C. They just keep adding onto each other. They're all related. Molecules hit harder, going to hit a greater force. But if they hit with the greater force, what would this wall do here? If a molecule is hitting this way and there's molecules, and it's hitting with more force in here. Do you agree that the wall will push outward? But then what would this wall over on the other side do? Push outward. And what would this wall do on the top? Push outward, right? And those walls will push outward. Everything's going to push outward. And if all those walls are pushing outward, what do we call that? And what is an expansion? Define the word expansion. Isaac, I'm looking at you. I don't know what your face is. See, this is why I don't like being in class with you, because I don't really know what your face is telling me. It's kind of like, it's not telling me anything.
Is it kind of when the box, so there's more area being.
It does, but what's a better way to describe it? Not area.
Pushing.
Show here, with your hands, show me an area.
So here's an area.
No.
No.
This is an area.
Okay.
That's a plane, right?
Yeah.
What's getting bigger?
The space.
Which is called a what? Area is 2 dimensions. What's 3 dimensions? Starts with a V.
Hard.
I'm not sure.
Volume, right?
Yes. Oh, I thought you said the letter B, not V.
Oh, well, then you're like box. No. So area, right? This is an area. This is a volume.
Yeah.
Now, do you guys also understand why I ask you to show me with your hands things? I want you to think about that for a second. Why do I ask that? Again, this is about learning. You're in college. Hopefully you guys are going to get 4-year degrees or more. So why am I asking you to show me with your hands? What does that tell me?
That we can like express ourselves.
Yes. Why do I care to see what is that telling me when you show me?
It shows our understanding of the topic.
Kind of, but I'm really more concerned to see how you're thinking. If you're thinking in this, and you should be thinking in this, you're in the wrong spatial dimensions. See, because I don't know what you think. I say words, and I don't know what you think when I say those words. That's what communication's about, right? I say a word, and you have an idea in your head. And a lot of times, you will talk to people who will be thinking something different when I talk. And I need to know what you're thinking. So if the volume is getting bigger, then you would say what? You say the volume is getting larger. If the volume gets larger, do you agree that the areas of each side get larger also? But since pressure is force over area, what would the pressure do as the box gets larger? The areas would also get larger, and therefore the pressure would do what?
Stay the same.
Now, what would the pressure do? Well, actually, Tim, you might be right. What does the pressure do if this box got larger? The areas get larger. Would that make the pressure go down? If this gets larger, and this stayed the same, that would go down.
Yeah, but if their force and area are changing, the pressure would.
Okay, right, but didn't we say that we're making the force larger also, and the area is getting larger, but the box will expand so that the pressure inside is equal to the pressure outside, and therefore the pressure can stay the same.
Okay, I think I was just a little ahead there.
Well, no, what's interesting is you thought a different way than I was going, which is fine, because I understand that.
Okay.
So when I heat a gas, do you agree I'm going to make this box expand? So here's the question. Why does the gas expand and cool? Isn't that what I said we were going to talk about? Why does a gas cool when it expands?
Is it because the molecules are hitting each other, so it causes friction and they
Okay,
slow down?
let's stop for a second. Okay, let me just think about this, because everybody wants to say this. I think, Tom, you said this last week. You talked about collisions. Rub your hands together like this. What exactly is going on? Why does it get warmer?
Transfer of energy.
What do you, be more specific?
Kinetic energy to, I don't know, heat energy.
Did I talk about the 3 methods of transferring heat in this class? Have I talked about that? Okay, so let's do a side note on this. There's 3 methods of transferring heat. Actually, heat is the transfer of energy. So I want to think of heating, like a verb. I'm heating something. I do not, listen to me, I do not want to think of heat as a noun, not yet. Heat is not a noun. Heat is a verb. I'm taking energy from something to something else. There are only 3 methods of heating. One of them is called conduction. One of them is called convection. And one is called radiation. Right? Radiation are things called electromagnetic waves. If I set up an electric field, I get a magnetic field. Electricity and magnetism are related. I sucked at this when I was your age. I was bad in college. I was bad in high school. There was a friend of mine back in, like, I don't know, junior high. His name was Steve Pahovy. And he had a, I hope nobody knows Steve Pahovy. He had this big honking nose. It was a big hook-billed nose. And he was just kind of a geeky kid. And, you know, he wasn't athletic. I mean, he liked sports and stuff, but he was just a geek. He really was a geek. And you know what he used to play with? Those little electric circuit boards. And I remember him wanting to play with that. I'm like, gosh, I want to go, you know, I want to have dirt clod fights, or I want to go play kickball, or I want to go play baseball, or I want to play football, whatever, right? I just want to do stuff. And he was like, no, I've got to think, I'm going to do this stuff. And I never really understood this. And then after graduation, he's like this electrical engineer, and he's making hundreds of thousands of dollars a year. He's probably one of the more wealthy of my high school graduates. So he kicked everyone's butt while I was throwing dirt balls at people, or snowballs at people. He was thinking about electricity. And I remember, I don't really understand electricity. Do any of you guys work with circuits? Like, you know, transistors and resistors and capacitors and inductors and stuff? Are any of you guys good at that?
I mean, I took a class on it like my sophomore year of high school, so I know
Did
a
you-
bit about it.
Do you ever play with stuff like that? How many of you, do you guys know people like this Steve Hovey, really geek, and they always are playing with weird stuff like that? I mean, it's kind of fun. I like those people. I didn't realize I wish I were like them, but I was kind of a slacker when I was younger. So electromagnetic waves, these are radiation. We're going to talk about visible light, infrared, ultraviolet. We have an entire unit on radiation coming up. The sun, do you agree that the sun gives off radiation? The earth, all objects give off radiation. The earth is giving off radiation. We're all happy with this. Okay, radiation. This is important. That's one of the ways of transferring energy. We're not going to worry about that for a little while. Now, conduction is the transfer of heat from warm to cold by contact. Things touch and they transfer heat. We call this sensible heat. So if we talk about the term sensible heat, to sense something is to touch something. So I always like to start with this, just kind of interesting. Right now, touch a piece of paper or a piece of wood or something. Okay, now touch something metal. Which is colder?
The metal.
Lena, did you really just say that?
Okay, well, it feels colder.
Right. What temperature is the metal thing that you touch?
The same temperature as everything else in my room right now.
The same temperature everything else is, right? They're all the same temperature. But do you agree that the metal feels colder? And that's because your hand, being warmer than the object, will lose heat to the object. You are transferring heat, energy, from one thing to the next thing. And metal will allow you to conduct heat much faster. Metals are good conductors. You ever cook a baked potato in aluminum foil? Do you just grab it in the oven with your bare hand? No, that would be bad. But if you put it on your plate and you could get a little corner and unroll it, couldn't you touch the metal instantly after you unroll the potato? That's because metal loses its heat to the air really, really fast. It's a good conductor. Now, air is a poor conductor. Every time I see this word, I think of the following line. What movie? He chose poorly. What movie is that?
The Indiana Jones, Last
Indiana
Crusade.
Jones. Yeah, the last one with Sean Connery and stuff. If it's a poor conductor, it's a good what? What's the opposite? It's a good insulator. So air insulates. That's why you have hair. That's why you wear clothes with layers, because you're trapping air around your body. You have hair, even on your arms, you've got hair, and the air comes in contact with your skin and it stays warm. So what's the best way to lose that heat? Blow the air away. That's what wind chill is. But blowing the air away is convection, which is the transfer of heat within a fluid by fluid motions. So transfer heat within a fluid by fluid motions. A fluid is something that flows. Do you agree that liquids flow? Air also flows. So I'm transferring the heat within a fluid. So imagine that I'm in a room. Here's the room, and over here it's really cold, and over here it's warm. If I'm standing over here and I'm too warm and I got to get the cold air, what do I want to put on? How do I get this air over here? You put on a fan, right? So you put a fan and it blows the air. And so what you're doing is you're redistributing the fluid. You're mixing warm air into the cold air is into the warm air. It's mixing up. That is called convection. Now, one little note here. A physicist goes convection, three-dimensional, all moving. A meteorologist says if it's horizontal, we're going to call that advection. And if it's vertical, we're going to call that convection. So to a meteorologist, convection and advection are going to be a little bit different. They're all basically this overarching principle of convection. Okay. Now, this box doesn't allow which one of these things primarily. Which one of these things is not allowed in my parcel? Remember, this is all what we call parcel theory. So which one of these three is not allowed? Ryan?
I'm not sure.
What do you think, Bobby?
Would it be conduction? Because is it an imaginary box or?
Yeah, I mean, in reality, we're going to say conduction doesn't matter also because air is a poor conductor. So we're going to pretend that conduction doesn't take place. But which one, by definition, based on what this is, doesn't take place? Because what kind of a box is this? It's a Vegas box. And remember, if this air were cold and this air was warm, convection would be moving air in and out of the box. But this is a Vegas box and that's not allowed. So by definition, convection doesn't take place. Does that make sense to you guys? Do you understand what I'm saying? Okay. So when I heat a gas, it expands. So how can you imagine heating this gas, heating this box? What's the easiest way to kind of picture heating it?
Heating stove.
Put it on the stove. And what kind of heating would a stove be? When you put something on the stove, what kind of heating is it?
Conduction.
Well, it depends what kind of stove.
No, either way. Even if it's gas stove, it's still conduction, isn't it? I mean, you're heating the water because the flames are coming in contact with it. I mean, you could turn on this gas and move the pan of water over here, and it's not going to get warmer. You have to put it on it. So stoves heating are conductive. Now, do you also agree that maybe the sunlight can come and heat it?
Yes.
So you could imagine that, but the easiest way is put it on a stove, put it on a fire. If you heat that gas, what's it going to do? It's going to expand. You increase the kinetic energy of the molecules. What's the formula for kinetic energy, everybody?
1/2 m times v squared.
1/2 times mv squared, and then, or 1 times m times v squared. And they move faster, so they're going to hit the walls with greater momentum. Their momentum is going to change more, which is a greater force. The force is going to act on the walls of the box to push the walls outward in an expansion in 3 dimensions. But the idea is that the pressure's got to stay the same as it is outside because it's an imaginary box. So the box expands, the molecules move faster, the volume gets larger, the area gets larger, but the pressure stays constant. Why, when you're doing this, what is going on here? Is there heat being transferred? What makes something warmer? It has to have more what?
Kinetic energy.
Kinetic energy. Where's the kinetic energy coming from? Me. I'm moving my hands. Now go like this. Does that feel like this? Is that feeling warmer? When you put them together, does it feel warmer? Do you agree that you have to exert more effort, because if I let it go, the kinetic energy would be used up. I'm using kinetic energy to get things hotter. So what's getting warmer are not my hands per se, but the molecules in my hands. I'm transferring kinetic energy from this motion to the molecular level, making it hotter. But do you understand, like anything else, if I took, here, I think I can actually use this. I take a car and the car is rolling along. If I let it go, what will the car eventually do? When the car eventually stop? Why? What happened to the kinetic energy?
It was exerted onto the ground.
It exerted on the ground. Do you agree that the tires and the ground would have gotten a little bit warmer, but the car slows down? I'm using the kinetic energy, and therefore the car slows down. Now you're telling me that molecules hitting each other have kinetic energy, but you see why that can't be possible. Why is it that you cannot talk about kinetic energy of the molecules getting used up when they hit each other? Because if the molecules hit each other and lost kinetic energy, what would the temperature of the molecules become? Hey guys, watch my hands. I'm using, the friction is causing them to slow down. What's my temperature? Going up. If these were two molecules hitting, if you're saying that there's friction, then the molecules would get warmer. But getting warmer means they go faster, and you're telling me it goes slower. So here's the thing about about partial theory and kinetic energy. Molecules hitting molecules doesn't change the kinetic energy. Molecules hitting molecules does not change energy. There is no friction at the molecular level. There's a name for that type of collision. It's called elastic. Has anybody taken physics? Tom, have you taken physics?
High school.
In high school? Have you ever heard of the term elastic collision? It just means you're not losing kinetic energy, because it doesn't make sense. So why does a gas that expands cool? That expands cool.
Is it because the box is using energy to expand and losing heat? Or losing temperature?
Unpack that for us.
It's hard to, but I'll try. Like, I'm thinking of like when you burn some sort of, or heat up metal to where it's like almost molten, and you're able to like change the shape of it. But as you're changing the shape of it, it kind of cools down. So maybe the heat is transferred over a larger area. I don't know.
Okay, I understand what you're doing. It's good thinking. You're not completely off track. Here's the thing though. When I heat a gas, I say that to you. What do you say in your head? What do you see? What's your abstract conceptualization when I heat a gas? Avi, what do you say to that? What do you see?
Well, I would imagine the molecules moving faster.
Why is that? Here, take a gas, heat it. What are you doing to it? What's your picture? And you just going on a stove?
Yeah.
Okay, so in other words, that's what you see in your brain. Oh, okay, I can take this box, put it on the stove, and I'm giving it heat, and now it's going to expand. And I think we get that. I think you understand that. When a gas expands, how do you make it expand?
Going to be the molecules hitting the walls of the given box and making that expand.
Why is it doing that?
Because it has more kinetic energy because it's being heated up.
Oh, wait a second. Did you hear what he just did? Think about what he just did. That can't be right.
The energy.
Okay, listen to this. This is important. When you heat a gas, the cause is I'm heating it. What's the effect? Expansion. The cause is heating, the effect is expansion. When a gas expands, expansion is the cause, and then what's the effect? The gas gets colder. If you say, well, it expands because you're heating it, then you're doing the first set of things, not the second set. You have the wrong cause. So you have to ask yourself, why does the gas expand? Why does the gas expand? Now, do you agree that you could heat it? But if you heated a gas, it would expand. It would get warmer, wouldn't it? Because I'm heating it. So why does a gas expand? How do I make a gas expand? It's amazing what your brain can do if you think about things. It's like, whoa. Did you find the mystery? That here, everybody grab a box. Pretend that there's a real box in your hands. How would you try to make it expand? Okay, so imagine that I have this box and I pull the sides of the box like this. What would the other sides do? When the other sides get smaller, so would I change the volume? I would make these two sides this length bigger, but the other things would get smaller. So if you take a box and you just try to stretch it, it's going to be the same volume. Like a balloon, right? I have a balloon, I squeeze it, it changes its shape, but the volume's the same. So how do I make a box expand? I like this. This is one of my favorite things to do because it's just interesting. Go to your rooms and you figure out, how do you make the gas expand? And then why does it get cooler? So have a discussion. And really, because you know what you're going to get? You know what you're going to get when you start talking to each other? The wrong answers. You're not going to be right. Nobody ever is. You got to figure it out. But you got to start processing that information. Get into the area where you're wrong and say, okay, what? And try to figure it out. So I'll give you a couple minutes. Why does the gas get the gas to expand? And then what happens when it expands? Okay, bye. And I will pause. Shoot. So I forgot to record this. Oh, well, you guys should be in class because it's a virtual class. You did not transfer heat away from the box by conduction, by convection, or by radiation. And so I was recording this and I forgot to unpause it. So it's there for you, but I'm sorry, we missed that little discussion on it. So if you were not in class, you need to be in class because it's still a virtual class. This is just a benefit to you. So I want you to imagine that this is a real class that we're meeting at school and we have to meet every day. Okay, attendance is necessary. That means this. Share my screen. Draw on here. I'm going to take this away. I've got no conduction, no convection, no radiation. The word for that is adiabatic. A is a prefix that means no. Diabatic refers to heating. So when I lift this box, there is an adiabatic process. There is no heat coming in or out of the box. It is adiabatic. Okay? Say that word, adiabatic.
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 It's like the number 80, abatic. Everybody say it.
Adiabatic.
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 And it means no heat. So there's no heat transferring in or out of the box. But it still has less kinetic energy. So where did it go? Well, let's think about things for a second. What is energy used for? Why do you have energy? What does energy allow you to do?
Movement.
Well, movement.
To
Something else.
exert force.
When you exert force, what are you doing? Why does your car need gasoline? What does an engine do? Doesn't an engine take in gasoline and do what?
Burns it.
Well, it does burn it, but what do you call an engine? An engine does what?
Creates power.
Close. It does
Work.
work. That's what it's called. An engine does work. You use the engine, you burn the gasoline, you take the energy to do something. What's the work of a gas? Expansion. It takes energy to expand the gas. Now think about this. Remember we talked about the kids in the small room? If we put the kids into a larger room, do you agree they would just run, they'd run as fast as they did in the small room, they just wouldn't hit stuff as much. But what if I said, hey kids, push the walls of the room, make the room bigger. Then when they start running around, they're going to be tired and they're not going to have as much energy to work. I mean, they've already expended the energy to cause the room to get bigger, and they're going to run slower. So the molecules are taking their kinetic energy, pushing the walls of the box, and then making the box bigger. Therefore, they have less kinetic energy left over, which means it's colder. Isaac, do you understand what I've said? Can you repeat that in your own words?
I'm really sorry. I did just zone out a little bit.
Well, okay. First of all, I'm not upset that's happening to you. I just need you all to be able to repeat that. Somebody repeat it. Who wants to try it?
I could try. So
So, Zach, what I want you to do is I want you to look at Isaac, well, if you can, and teach him.
So when you have an interaction or a force, it takes energy to cause that force. Like for example, it takes energy to rub your hands together. Like you are spending energy that you have to rub your hands together, and that creates heat. And so as the molecules hit the walls of the box and makes it expand, it's costing energy or it's heat to expand the box to give it a bigger area to move around, so it causes the molecules to move slower.
Don't say area.
Or a larger volume for the molecules to move around inside that box, so they slow down from spending that energy.
Okay, now a couple things, because remember, what am I trying to teach you in this class more than anything else?
How to learn.
How to learn, how to
think,
right? I want to point out something, Zach, that you did. He said area. Do you understand? He got the wrong thing. And I said, no, that's not right. Did you see the way he goes, oh, no, I meant volume. He knows, your brain knows what the right answer is. It's communicating something differently. But that's why if you really want to learn something, you need to speak. How many of you are psychology majors? Is anybody a psych major? Have you ever taken a psych class? One of the great things they talk about the different hemispheres of your brain. You have different areas in your brain that control different functions. And they do this experiment. It's really awesome. People who have seizures, grandma seizures, grandma, something like that. Do you know what they do to cure them of these epileptic seizures? Does anybody know? They split the brain in half. They separate the two hemispheres of the brain. And supposedly that stops these seizures. The problem is your brain needs to communicate with either side of it. So sometimes people have strokes. Have you ever known somebody to have a stroke? And when they're recovering, they often have a hard time speaking. And I knew of this one woman who would do this. You would put a pen in her right hand and you say, what is that? And she's like, oh, God. And she couldn't think of the word. She goes, you write with it. And then they put it into her left hand or vice versa, maybe see it vice versa. And she goes, oh, that's a pen. Because it's controlling a different part of your brain that the word pen is there. The knowledge of what a pen does is in a different part of your brain. And your right hand is affecting your left side and your left hand goes to your right side. So it needs to communicate with each other. And they can do that by blocking out and testing you with one eye versus the other eye, because you're stimulating a different part of your brain. Now, do you understand what I'm saying is that if she knew one hand was a pen writes and the other one, she goes, that's a pen, and she couldn't come up with the word, that means your brain needs to communicate to each other, which means different parts of your brain are storing different elements of information. You have lived your entire, I'm going to say this because I'm being snarky, your entire stupid life, probably sitting in a classroom, listening to a teacher, blah, 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 and you just write your notes down. And what I'm telling you is this, is that you want to learn, you need to start talking. You need to speak through the information because your brain has a different part of it that it's getting input and you're memorizing things and you're learning things. And what's amazing, and Zach, you did this exactly, is when I said that's wrong, you immediately fixed it. And with assuredness, right? You went, no, I meant volume. It's amazing how you self-correct when you speak. When you try to force something out, there's a lot of you like, yeah, that's not right. Let me try that again. That's learning. Learning is active. It is not passive. So that Zach started to explain things is helping him because now he's formulating words. Isaac, that's why when I asked you, I don't care that you don't get it because you're probably afraid that you're not getting it. So you speak it out and then see what your brain says when you say things that are wrong. Does your brain correct it? People who talk out loud are often much harsher critics of themselves. They're like, no, that wasn't right. Well, okay, then fix it. This is what I mean by active learning. So think about this. I am heating a gas and I expand. We got that. Now it's expanding. There's molecules. What do the molecules have? Do this. What is this that I'm demonstrating?
The speed of the molecules.
Which is the what of the molecules?
Um,
Give me a better word.
Momentum.
Well,
Okay.
momentum is better.
Wait.
What do they have? Kinetic energy. 1/2 the mass times the velocity squared. As they're pushing the wall of the box. Do you understand? To push the wall of the box takes force, takes effort. The effort comes from the energy of the molecules. If they move the wall, they're imparting some of the energy into the wall to push it out. They're actually, now Tom, this is kind of what you said before, they're actually pushing the molecules outside of the box away. And it takes effort to do that. Do you agree that in order to do work, it takes effort? Now, imagine that you have a big rock in your path, a big boulder. How much work do you have to do? Depends on what two things. If you're going to move the rock.
The weight of the rock.
How big the rock is, right? The mass, the weight of it. And what else?
How much energy you can force on.
Yeah, there's something else. I mean, it's pretty simple. If I said, hey, Tim, move the rock a couple of inches. You'd be like, oh, okay. If I said move it a mile, would you agree that kind of sucks? That would be a lot more work to move it a mile. So it's not just the work to do the mass of the rock, but how far you move it.
Okay.
The further you move it, the more work you have to do. And you're expending energy to do that work. Okay? Now, what if you're on a hill and the rock is rolling down the hill and you're just pretending to push it? Are you doing any work? If the rock, you're just pretending to push it and it's rolling on its own? No, you're not doing any work, because work requires what? What does the rock have to do to you to do more work on it?
Exert a force back.
Yeah, there's a big, yes. And what do you call it when somebody exerts something back at
A reaction.
you? Think about it in terms of political. If somebody's not going to follow you, they're going to give you what? Isn't that what resistance is? The rock, the more that it resists you, the more work you have to do to move it. That's what resistance is. I'm not gonna move. The bigger the rock, the more the resistance. If it's moving on its own and it's not resisting me, it takes nothing. So this box expands. What's resisting the box from expanding?
External pressure.
Isn't there external pressure? If it's resisting, then any expansion requires energy. Where's the energy coming from to do the work of expansion? Write that down. Where's the energy coming from to do the work of expansion?
Can you repeat that one more time?
Where's the energy coming from to do the work of expansion?
We're supposed to answer this too.
Well, yeah. Give me the answer. What do you got?
It's coming from the particles or molecules
It's
inside
coming
the
from
box.
the molecules themselves, right? And in order to do work, you have to have what to do work? Energy. Energy comes from the molecules. What kind of energy do the molecules have? Kinetic. If I use the kinetic energy to do the work, then I have less kinetic energy. What do you call the measure of kinetic energy? Temperature. The gas. Now, just for the sake of it, hold on. Let me move you guys back over here. Let me draw a little picture on here. Work, by the way, has a formula. Anybody know what the formula is? What is this?
Force.
Times
Distance.
distance. Force times distance. I have a box. And the box is expanding. This corner moves outward. It's a change in the distance. This one would be a change in the y distance. This is a change in the z distance. That's the distance. That's the thickness. And a change in the x distance times a change in the y distance times a change, oops, in the z distance is a change in volume. Because volume equals delta x times delta y times delta z, which we did the other day. So you see that expansion, which is the change in the volume, is work in 3 dimensions. Kind of cool. And Tom, at least I hope you, and I mean, I assume others probably appreciate this too, but mathematics makes physics better, easier sometimes if you know how to do the math. If you do the math correctly, it makes it simpler because you're like, oh, that makes sense. And some of you are like, I don't have that much math skills, but you get the idea that expansion is work. Now, here's the thing. Any questions before I erase this? When I lift this box, the box expands. So when I lift the box, what's the first thing that happens to it? Pressure decreases outside. Pressure inside has to be equal. When is the pressure inside equal to the pressure outside in this parcel, in this box? Always. So the box expands. So pressure goes down is 1, expansion is 2, and then number 3 is temperature decreases. It decreases at something called the dry adiabatic lapse rate. The dry adiabatic lapse rate, which is 10 degrees Celsius per kilometer. It's a fixed rate of getting cold. That means for every kilometer this box goes up, the temperature is going down because it's a rate of cooling, positive 10 degrees for every kilometer. What do you think? Does that make sense? There's a reason for this. I'm not going to go through it with you in this class. You just need to know it's 10. Fair enough? Okay. That's a Vegas box. That's the parcel of air. Here's a question for you guys. You ready for something freaky? Let's see. Let me stop the share for a sec. Imagine that you took a box of air and you suddenly put it into outer space. What would the box do? And what would it do? Tom said expand. Your mic's not working, but I think I read your lips saying expand. Do you agree that the outside, in outer space, there's nothing around you, so the box would expand? Would it get colder? How many people say it gets colder? Raise your hand. Aaron, you got your hand up?
Yep.
How about the rest of you guys? Lena's saying yes, it gets colder. Ryan, what do you say?
I mean, I don't know if there would be any conduction, convection, or radiation. And wouldn't there have to be?
First of all, Ryan, there are none.
Oh, but it would get colder because it would expand, right?
Well, this is true. So you say it would expand. Okay. Tim, what do you say? Oh, go ahead. What are you going to say?
Well, isn't like the only reason why it gets colder is because we're exerting energy to expand the box, but since we're in space, it's a vacuum. There's nothing outside the box to push again. So there's like, so it'd be like doing like 20 minus 0. So it would just rapidly expand and keep the same temperature, right?
Right, because what would the molecules in the box do? They'd be moving at a speed, right? And it would start moving out, but there's nothing to stop it because there's no outside. So the molecules just keep going without stopping. So all those molecules would they would go all over space, but their average kinetic energy wouldn't change. So in space, the temperature would expand, the box would expand, but there'd be no cooling because there's no resistance. Remember we said you got to have resistance to do work? There's no outside stuff. So if you took that box of space, the temperature doesn't change, which is kind of cool. Now, what does all this lead to? Remember I told you if I were king, there's certain things I'd want you to know. Did I say that to you?
Yes.
What was the first thing I said I want you to know?
Newton's second law.
Correct. Here's the next one. Oops. This is my favorite law of all time, because it's so interesting to me. Heat in. When I add heat to something, it can do work. In a gas, that's expansion. And it gets warmer. Do you agree? When I add heat to a gas, it expands, but it also gets hotter, doesn't it? That's the first law of thermodynamics. Probably one of the most important things in all of the universe. This is always true. So in an adiabatic process, what is the adiabatic form of the first law? What would this equation look like if the process is adiabatic? How would this equation change in an adiabatic process?
Well, there's no heat in.
Well, if it's no heat, how do I write that? 0 equals work, right? Could I write that something different? Couldn't I just say that work work equals negative change in temperature. So in other words, when a gas expands, temperature gets colder. When a gas expands, it gets colder. That's the first law of thermodynamics in an adiabatic process. That makes sense? If I took the box into outer space, what would this equation look like? What would this equation look like in space? What do you think, Nick?
I have no idea.
Well, if I took this box of space, do I add any heat?
No.
Okay, so 0. Does it do work?
No.
Does it change temperature?
Yes, right?
No.
Or, no. Okay, then no.
0 equals 0 plus 4. That doesn't make
Oh,
sense.
well, yeah, I guess. Yeah.
0 equals 0 plus 0. That's what that equation is in space. This is called Joule's law. There's an actual name for that. It's kind of cool. You ever heard of a joule? It's a unit of energy. Joule, the energy units were named after Joule. So this is what Joule figured out. 0 equals 0 plus 0. Wow, thanks very much, Joule. Really insightful. But that's the first law of thermodynamics. And I would not let a student come out of high school without knowing this, because I think they should. Questions on this? Scale of 1 to 5, how well do you understand? Show me. Okay, I've got a bunch of 4s. 3, Nick.
Yeah.
Isaac, you'll have this online except for that one little section. Aaron, what's her number?
4.
4, okay. Well, this is all there. Oops, sorry. This is all this is all there for you to do stuff with. I think it's pretty cool. It's kind of important. And then next time, what we're going to do is we're going to say, okay, well, what if we lift a parcel and we know how the parcel changes its temperature? What happens to the environment around it? What if it changes? And then we need to discuss that. So we still have some relationships that are really important. So what I want you to do for Thursday, some of you have your stuff to turn in. You're going to get points taken off, but you need to turn the points. You need to turn the stuff. Okay? For Thursday, the rest of you, you need to start doing chapter 2. And you also need to answer the following question. So let me just do this real quick, and then I'll let you go. Oh, wait, I suppose I need to show you something. Hold on. Share the screen. We have 3 important variables in the atmosphere. P stands for what?
Sure.
What Greek letter is that?
Rho.
Stands for?
Density.
And temperature. Do you understand that there are 3 relationships? Three variables, 3 sets of relationships if you hold the third constant. What are the 3 relationships in this? And I want you to think through it by imagining the box. So you say, keep one of them constant, change the other. Okay? Does everybody understand what I'm asking? So try to figure that one out, okay? And with that, you have any questions? You guys did a great job today. Isaac, don't lose confidence. Go back and figure those things out. You'll get there. But remember what I said about now you try talking. Talk to yourself about it out loud, okay? That'll help you. Okay, guys. Thumbs up. I will see you guys on Thursday.
Thank you.
Bye-bye.
Thank you.